Hello to everyone. So we are going to see algebra number theory concepts. What is the objective of that? To introduce the basic notions of groups, rings, field, which will then used for some related problems. To introduce the apply the concept of rings, finite fields, and polynomials. To understand the basic concepts in number theory, to examine the key questions in the theory of numbers, to give the integrated approach to number theory and abstract algebra, and provide a firm basis for further reading and study in the subjects. Unit 1, Groups and Rings. These are the topics we are going to study under groups and rings. Definition, properties, homomorphism, isomorphism, cyclic group, cosets, Lagrange's theorem, and these are under the group concepts. And next, the ring concept, definition, subrings, integral domain, fields, integral modulo n, etc. Next. So before that, what is a binary operation? The star operator star is said to be a binary operation on the non-empty set A if A star B belongs to A for all AB belongs to A. So closure property should satisfy for binary operation. So binary in the sense two elements should be operated in between that. That's all. Algebraic system. A set A with one or more binary operation defined on it is called algebraic system. For example, n is the natural number starts from 1 under the binary operation plus. And z is a set of all integer under the two binary operation plus minus. These are called the algebraic system. We are going to discuss the properties of binary operation. Number 1, star is a binary operation on the closed empty set A. Number 1 is closure. The binary operator star is said to be a closure property on a non-empty set A. That is, A star B belongs to A. We are just collecting two elements from A. If we operate on that, that element should be again belongs to that capital A. That is called closure. Associative. The operation star is said to be an associative. That is, in closure, we just took the two elements. In associative, we have to pick three elements. The A star, B star, C, just interchanging the brackets, it is associative law. Next, identity. Identity is element E is said to be an identity element such that A star E equal to E star A equal to A. That A, that identity element is also belongs to capital A. That is the identity of that group. Inverse. A star, A comma star is algebraic system with identity E. Let A be an element in A, that B is said to be inverse of A, that is A star B equal to B star A equal to E. That is, A inverse is said to be an B if the equal to identity element should exist. If the condition satisfied, then it is said to be an inverse condition. Next, commutative. So commutative is nothing but the A star B equal to B star A is called commutative. So these are some of the basic properties of the binary operation. Next, these are some of the types of algebraic system, that is semi-group, monoids, groups, subgroups, normal subgroup. Number 1, there are 5 properties of the algebraic system. Number 1 is closure, associative, identity, inverse, commutative. Suppose in the group, if closure and associative alone satisfied, then you can say it is said to be a semi-group. Suppose if closure, associative, identity is satisfied, then you can say to be a monoid. Then closure plus associative plus identity plus inverse is satisfied, then you can say to be a group. Suppose closure, associative, identity, inverse, commutative. All those things are satisfied, then you can say it is an abelian group. So this is the main conditions types of algebraic system. Once again, I repeat, closure and associative. First two properties are satisfied, then you can say to be a semi-group. 3 conditions are satisfied, then it is said to be a monoid. 4 conditions are satisfied, then it is said to be a group. If all the 5 properties are conditions are satisfied, then you can say it is a abelian group. Semi-group. Already we told star is a closed operation. such that only two conditions, closure and associative, are satisfied. Monoid. Star is a binary operation under the A is a group under the binary operation star is said to be a monoid, such that three following conditions are satisfied. Number one, closure, associative, identity. So we are just introducing the definition of group. So algebraic system G comma star is said to be a group if star is a closed operation. First, it should be a closed operation. That is, it is a closure condition should be satisfied. Second, associative. Third, identity. Fourth, inverse. And if all the four conditions are satisfied, you can say it is a group. And the extra commutative condition is satisfied, then you can say it's a abelian group. So this is a diagrammatic approach of the algebraic system. So overall, it is algebraic system. It's a universal set. So in the universal set, what is the other subset is semigroup. Subset of semigroup is monoid. Groups, abelian group. So it's all together is under algebraic system. Next, order of the group. The number of elements in the group is called the order of the group. Suppose in the group there are only two elements. The order of the group is said to be equal to 2. So number of elements in the group is said to be a order of the group. Finite group. If the group of the element is finite, you can say it is a finite group. Otherwise, it is an infinite group. Next, let G comma. Next, you can say order of an element of a group. Order of the group is different. Order of an element of the group is different. Suppose if you are choosing one element from the group, suppose if you are express that element in terms of a power n equal to e. Suppose if you express in the element a power n equal to e, that a is said to be a order of that group. So order of the group, number of elements in the group is called the order of the group. Number of elements of the group is nothing but if you choose one element from the group that can be expressed as a power n equal to e, that a is said to be a order of an element of a group. Next, we move on to the problem. Problem 1. Show that set of all integer is an abelian group with respect to the addition. We have to check whether the set of all integer is an abelian group or not. What is the meaning of abelian group? 5 conditions should satisfy. So we have to check all the 5 conditions. So first, what is a group here? Set of all integer. Integer is nothing but minus 2 plus including 0. It is a set of all integer. So closure property. Suppose, for example, if you choose two elements from the under the relation, what is a binary operation we are using? Addition. So G comma plus G is nothing but Z. So Z comma plus is an abelian group or not? We have to check it. First one is closure. Suppose in the integer you choose any two elements, 2 comma 3. If you add 2 comma 3, 2 plus 3 is a 5. 5 is also belongs to integer. So closure is true. Associative. Choose 3 elements, 2 comma 3 comma 4. Suppose 2 plus 3 plus 4 now. 2 plus 3 plus 4. You can just interchanging the brackets. So obviously it's same. So associative is also true. Identity. In addition, identity is nothing but 0. So 0 plus 5. 5 is an element chosen from the group. So 0 plus 5 is nothing but 5. That answer is also belongs to the group. So 0 is the identity element under addition. Next, inverse. So inverse is nothing but you have to under the addition, the inverse is minus. So if you choose the element A, the inverse of A is nothing but minus A. So A plus of minus A is equal to the identity element. What is the identity element under plus is 0. So condition is satisfied. So inverse of A is minus A. This is also true. So all the 4 conditions are satisfied. Only another condition is commutative. Anyway, A plus B equal to B plus A. So 2 plus 3 equal to 3 plus 2. Anyway, the conditions are satisfied. So all the 5 conditions are satisfied. Then you can say it is a abelian group. Therefore, Z comma plus is an abelian group. This is a very beautiful example starting of the group. Next, problem number 2. Show that set of all non-zero real number is an abelian group with respect to multiplication. So here by a group is a non-zero real numbers under the binary operation star. Star is nothing but multiplication. Anyway, we have to check all the 5 properties. If all the 5 properties are satisfied, then you can say it is a abelian group. If any one is failed, you cannot say it is an abelian group. Number one, closure property, same as per the problem one. You have to choose 2 elements from the set of all non-zero real number, 1 comma 2. Obviously, 1 dot 2 equal to 2. The 2 is also belongs to R star. Associative. So same as per the closure property, we have to choose 3 elements. A, B, C belongs to R star. So if you operate any elements under the operation dot, the answer will be same. So associative is also true. Identity. Identity, obviously, under the multiplication, one is a identity element under dot. So A dot 1 equal to A. A, B, any element from the non-zero real numbers. Inverse. So here it's very important. So in real numbers, fraction is also under the real numbers. So if you choose the value 5, what is the inverse of 5 under dot is 1 by 5. That 1 by 5 is also belongs to non-zero real number. Anyway, the inverse condition is also satisfied. And then commutative. Commutative is obviously true because if you multiply two real numbers, obviously the real numbers. So 2 dot 3 is equal to 3 dot 2 equal to anyway the same value exists 6. So all the 5 conditions are satisfied. Therefore, you can say set of all non-zero real number under multiplication is an abelian group. It's a very beautiful example. Next, problem number 3. Show that set of all real numbers R is not a group with respect to multiplication. So we have to check it's not a group. It's not a group means maybe a semi-group or monoid. We have to check whether it is. So the set of all real number is a group under the binary operation dot. So anyway, you all know 0 belongs to R. The multiplicative inverse, because 0 inverse is does not exist. Therefore, obviously, R is not a group. Anyway, it may be a monoid. Next, fourth. So same thing we have to check for the matrices. Set of all non-singular matrices, order n cross n, then show that M is a group with respect to matrix multiplication. So closure is if you multiply 2 under the multiplication, okay? If you multiply 2 matrix, the resultant will be also a matrix. If you choose a 2 by 2 of A and B as a 2 by 2, the resultant also is a 2 by 2. Obviously, closure is true. Associative, same thing. If you choose the 3 matrices and if you multiply any 3 matrices, there will be a matrices. So second is also same. Identity element. Obviously, identity element of the 2 by 2 or 3 by 3 is depends upon the order of the matrix is true. So inverse, obviously inverse exists because A inverse equal to I. It's a standard property you all know. But so all the 4 conditions are satisfied, you can say a group. But whether this matrix is belongs to abelian group or not, because commutative is always fails under matrix multiplication. Because if you multiply A dot B, it's not always equal to B dot A. It's a obviously you can say matrix multiplication is not commutative. Therefore, multiplication of matrix multiplication of order n cross n is a group, not a abelian group. It's a beautiful example. Next, fifth problem. So before that, we saw the binary operation is given as general, but here they are mentioned as the we have to operate the two element A star B should operate by AB by 2. The question is given itself, the question itself, they given the condition. You have to operate the A star B as AB by 2. That is first term into second term by 2. Under this operation, how we find the abelian group or not. Suppose set of all positive rational number forms a abelian group under the composition star. You consider the group as a positive rational number. Closure is always true because A star B is nothing but AB by 2. Obviously, it belongs to the group. Associative, same. So here the A star B, according to the condition, how can you write as A star B, AB by 2 star C? According to the again the condition, first term is a AB by 2, second term is a C. What is the removal of star is first term into second term by 2. So AB, C by 2, again it's a 2 by 4. Same, the bracket alone interchange. B star C can be written as a BC by 2. Again, you have to remove the star ABC by 4. Next, identity. According to the identity, what is the definition of identity? A star E equal to A. So according to the definition, what is the A star E? AE by 2. So AE by 2. And you can say E star A, that AE by 2 is also belongs to the group. So in identity is also exist. So AE by 2 equal to A. Obviously, by pre-multiplication law, A getting cancelled. Obviously, E equal to 2. That 2 is also belongs to the positive rational number, because any number can be expressed in terms of rational number. For example, 2 can be written as 2 by 1. So anyway, it belongs to positive rational number. So identity condition is also true. Inverse. Inverse. What is the formula of inverse? A star B equal to I. B is the inverse of A. According to the definition, A star B can be written as AB by 2. Obviously, E is equal to 2. If you substitute in that, AB by 2 equal to 2, B equal to 4 by A. 4 by A is a set of all positive rational number, right? So this is also true. So all the four conditions are satisfied. You can say it is a group. Commutative. So commutative, you all know A star B equal to B star A. Obviously, what is A star B? AB by 2. What is B star A? It's nothing but PA by 2. Both are same. So you can say set of all positive rational number under the composition star as defined as AB by 2 is an abelian group. It's a 8-mark question. Next, show that. Again, the beautiful classical example of the group is G can be written as a, see, this is the finite group because G is consisting of, this is called the cubed root of unity. Cubed root of unity is nothing but 1 omega square. So this is, you have to prove it is a abelian group under the binary operation dot. So in the above problem, we all define the group as a infinite because we didn't restrict the value of the group. But here, the group is restricted. The finite value is restricted. So what are the finite value is given in the 1 omega square? It's a finite group. So as per the previous definition, what is the order of the group is 3 because the group contains only 3 elements, 1 omega square. See, if it is a finite group, we have to form one table that is called Cayley table. So if it is a finite group only, we have to form it. For an infinite group, we cannot form the Cayley's table. So just we draw the Cayley's table. This is the Cayley's table under the operation dot 1 omega square. 1 omega square. Just multiply. 1 dot 1 is 1. 1 dot omega is omega. 1 dot omega square is omega square. Omega dot 1 is omega. Omega square. Omega square is omega cube. According to cube root of unity, as we know about the complex number, right? In complex number, what is omega cube value is 1 according to cube root of unity. So omega cube is not belongs to the group, but omega cube value 1 is belongs to the group. So we have to shift over the value as a 1. And then omega square into 1 is omega square. Omega square into omega always is omega cube. The omega cube value is 1. So we have to write the value as 1. Omega square into omega square is omega power 4. We can write omega power 4 as omega cube into omega. What is omega cube is 1. So 1 into omega is nothing but omega. So only thing is inside the table, all the values should be present in the group. So 1 omega square is alone present there. So closure property, if you take any two values, obviously according to the Cayley's table, you can say closure is true. Obviously, associative is also true. Identity element. What is the dot of identity element is 1. So 1 is also present in the group. So identity is also exist. Inverse. So what is the inverse is? See the table. 1. We have to check in that row where the 1 present. So 1 is present in the value of here. 1 inverse is 1. Omega in the row where the 1 present, the straight of omega square. So the omega inverse is omega square. Similarly, omega square inverse is omega. So this is the inverse according to the Cayley's table. And a commutative is always, the if you multiply two things, as values are same. So all the values are satisfied. Then you can say abelian group under the binary operation multiplication. So this is a beautiful example. And then what about the next problem? So what is the difference between the previous problem and this problem is, in previous problem, the group consisting of only three elements, one omega, omega square. And this is the fourth root of unity. What is the meaning of fourth root of unity according to the complex number is 1 minus 1, I minus I. We have to check whether it is a abelian group or not under the star multiplication. So first we have to analyze whether the group is a finite group or infinite group. Yes, the group of the element is countable, so therefore it is a finite. So if it is finite, what you have to first form? We have to form the Cayley's table. How to form the Cayley's table? Under the binary operation dot 1 minus 1, I minus I as a row, as a column. Just multiply 1 dot 1, 1 dot minus 1. So what is the I square according to the complex number is I square. If the value is I square, I square does not belongs to the group value, right? But according to the condition, what is I square equal to minus 1? We have to replace as minus 1. Got it? Next, if it is a I cube, then obviously I cube can be written as I square into I. So I square value is minus 1, so minus I. So we have to fix the value I square as a minus 1. Okay. And then if any power rises, I power 4 can be written as I square into I square. Minus 1 into minus 1 is obviously plus 1. That value belongs to the group, right? So we have to form the Cayley's table according to this rule. Got it? Next, what are the conditions should satisfied according to the abelian group closure? What is the meaning of closure? If we operate two elements, obviously it belongs to the Cayley's table, right? Closure is true. Associative is also true. Identity. Identity under the multiplication is 1. 1 is also present in the group. So obviously identity is also true. Inverse. What is the meaning of inverse? See, if we choose this one value, what is the corresponding one appear in that row is 1. So 1 inverse is 1. Minus 1 inverse is 1 appear here. So minus 1. I inverse is 1 is appeared here. So minus I. I inverse is minus I. Minus I inverse is I. So these are the inverse of that. Commutative is always true. Therefore, G fourth root of unity under the operation multiplication is an abelian group. This is the 8-mark question. Next question. This is also the same as per the previous one, finite group, because it's represented the matrix. Matrix is a finite group, finite or infinite. Here, the representation only the finite number of matrices, 1, 0, 0, 1, that values is given. So we have to check whether the form the abelian group under the matrix multiplication or not. So we have to label, because 1001 is identity element s. So we have to label it as I, A, B, C. So anyway, it's a finite group. If it is a finite group, what do you have to do? We have to form the Cayley's table. So Cayley's table, I, identity into identity. If we multiply any term, matrix by identities, become the value. So IABC, IABC. Just multiply IA into A. What is A into A is A square. We have to just multiply A square and the value will be I. So we have to form this Cayley's table according to general multiplication, matrix multiplication. Okay. Then we have to check whether all the conditions are satisfied or not. Closure. Anyway, if we multiply 2 according to the Cayley's table, obviously it is true. Associative is also true. Identity, obviously, its identity is present in the group 1001. So identity is also true. Inverse is also true. Commutative is commutative. We have to check. This is a main thing we have to check in the matrix. Because closure, associative, identity, inverse and all will be true, obviously, in the matrix multiplication. But we have to check, because we already saw the commutative of the matrices will not true.